Right now, a wall of charged particles torn straight from the surface of the Sun is racing toward Earth at more than 1 million miles per hour. Scientists tracking it are calling it a cannibal storm because it isn't one single eruption. It's two separate explosions that caught up with each other in space and merged into something far more dangerous than either one alone. And the unsettling part is this. The agencies watching it admit they aren't fully sure how strong it will be when it actually arrives, only that it could hit harder than the official forecast currently says. This whole event traces back to a single patch of the Sun's surface known as Active Region 4455, a sunspot cluster that turned violently unstable within the space of just a few hours. In the early morning, it fired off a powerful M9.3 flare. A few hours later, it followed that with another strong M7 flare. And before the day was even over, it unleashed a full X-class flare, the most intense category of solar eruption that exists. 3 major eruptions from the same small patch of the Sun, all within about 10 hours of each other. Each of those eruptions carried its own coronal mass ejection, a massive cloud of magnetized plasma hurled outward into space. Normally, these clouds travel on their own, arriving at Earth hours or days apart, each producing its own separate round of geomagnetic disturbance. This time, something different happened. The second cloud left the Sun faster than the first one, and because it was moving with greater speed, it eventually caught up to the slower cloud ahead of it out in open space. When a faster-moving cloud catches and overtakes a slower one, the two don't just pass through each other cleanly. They collide, compress, and tangle their magnetic fields together, merging into a single denser structure that scientists refer to as a cannibal coronal mass ejection. NASA researchers describe the result as complex ejecta, a tangled, reshaped magnetic structure that carries significantly more energy packed into it than either individual eruption would have delivered on its own. The difference matters enormously once this combined cloud slams into Earth's magnetic field. A single, ordinary coronal mass ejection might produce a mild or moderate geomagnetic disturbance, something most people never even notice. A cannibal ejection, with its tangled internal structure and amplified energy, has the potential to trigger a strong or even severe geomagnetic storm, the kind capable of pushing the aurora borealis far outside its usual polar range and putting real strain on the technology we depend on every single day. There's another twist buried inside this particular event that makes it even harder for forecasters to pin down. The sunspot, responsible for all 3 eruptions, region 4455, has what scientists call an anti-pale magnetic configuration. Under normal conditions, sunspots in a given solar cycle follow a predictable magnetic polarity pattern, one that forecasting models have been calibrated against for decades. Anti-hail regions flip that expected polarity in reverse, and they show up in fewer than 1 out of every 20 active sunspot regions. That reversed polarity creates unusually intense magnetic shear inside the sunspot itself, the kind of internal stress that builds towards sudden, forceful energy release. It's part of why this region managed to produce a full X-class flare, despite forecasters initially rating its overall complexity as fairly low. Standard prediction tools simply aren't built around this backward configuration, which means anti-hail regions have a track record of catching space weather forecasters off guard. If you're finding this breakdown useful, go ahead and hit that like button. It genuinely helps this kind of space weather coverage reach more people who need to understand it. Once the merged cannibal cloud was confirmed to be Earth-directed, the United States government's Space Weather Prediction Center issued a formal watch, warning that a strong Category 3 geomagnetic storm was likely, with a real possibility of escalating into a severe Category 4 event once the cloud made contact with our planet's magnetic field. Officials tracking the cloud were careful to note something important in their public statements. They had fairly high confidence the storm would actually arrive at Earth. What they didn't have was equally high confidence in exactly how strong it would end up being. That gap between confirmed arrival and uncertain intensity comes down to the physics of how these storms actually interact with our planet. The strength of a geomagnetic storm doesn't just depend on how fast a cloud is moving or how much material it's carrying. It depends heavily on the internal orientation of its magnetic field at the moment of impact, specifically whether that field is pointing north or south relative to Earth's own magnetic field. A cloud with a southward-oriented field connects far more efficiently with our planet's magnetosphere, unloading its energy in a way that can turn a moderate storm into a severe one almost instantly. Forecasters can't measure that orientation with real precision until the cloud is already close, sometimes only about 1 million miles away, leaving a narrow window to refine the warning before impact. To put the stakes of a severe storm in perspective, it helps to look back at recent history. Back in May of 2024, a cluster of X-class flares and at least 5 separate coronal mass ejections erupting from a single active sunspot region combined to produce a full Category 5 extreme geomagnetic storm, the first storm of that magnitude to strike Earth since 2003. That event pushed the aurora borealis as far south as roughly 21 degrees north latitude, visible in places that essentially never see it, while power grid operators and satellite companies spent days closely monitoring for damage. A similar severe storm struck again in November of 2025, driving auroras down into Arizona, Texas, and Florida, and causing radio blackouts across parts of Africa and Europe. Storms at that extreme level remain rare, but the broader pattern behind them is not rare at all right now, and that pattern comes down to timing. Earth is currently moving through the peak years of the sun's roughly 11-year activity cycle, a stretch scientists call solar maximum. During these peak years, sunspot regions form more frequently, grow larger, and produce dramatically more flares and coronal mass ejections than during the quieter years on either side of the cycle. The current cycle's peak arrived around the middle of 2025, and forecasters have noted that elevated activity is likely to persist into this year and potentially beyond, meaning cannibal eruptions and complex tangled ejecta like this one are increasingly likely to keep showing up rather than fading away. When this particular cannibal cloud finally made contact with Earth's magnetic field, it triggered a moderate to strong geomagnetic storm, noticeably energetic, but ultimately falling short of the full severe category some forecasters had flagged as a real possibility in the days beforehand. Skywatchers across a wide stretch of the globe still got a genuine show out of it, with the aurora borealis reported as far south as central England and Wales in Europe, and visible across a wide swath of the northern United States, wherever skies stayed clear enough for the charged particles interacting with oxygen and nitrogen in the upper atmosphere to paint the sky in green and red light. Even when a storm like this lands on the milder end of its predicted range, the underlying risks it carries are worth taking seriously, because the same charged particles producing those beautiful auroras are also capable of disrupting the technology sitting just above our heads and buried beneath our feet. Geomagnetic storms at the strong to severe level can induce unpredictable electrical currents directly into long power. Transmission lines and buried pipelines, currents that power grid operators have, to actively monitor and manage in real time to avoid equipment damage or localized outages. The same storms can degrade GPS signal accuracy for hours at a time, an effect that ripples out into aviation navigation, maritime shipping routes, and precision agriculture equipment that depends on centimeter-level positioning to function correctly. High-frequency radio communication takes a hit as well, since the same disturbed layer of the upper atmosphere that produces auroras also scatters the radio waves that pilots, ship crews, emergency responders, and amateur radio operators rely on for long-distance communication. And in low Earth orbit, the increased energy pumped into the atmosphere during a strong storm causes it to expand and thicken, adding extra drag to satellites and forcing operators to burn fuel adjusting orbits that would otherwise stay stable for months at a time. None of this is meant to suggest a single geomagnetic storm, even a strong one, poses some kind of civilization-ending threat, because it doesn't. Modern infrastructure, particularly power grids in regions with real experience handling these events, is generally built with enough resilience to absorb a storm at this level without lasting damage. What events like this cannibal eruption actually demonstrate is something more specific and, in its own way, more important. Even with satellites constantly watching the sun's surface and supercomputers modeling every eruption in near real time precisely, forecasting how a merged, tangled cloud of solar plasma will behave once it slams into our planet remains a genuine, unsolved challenge. It's worth remembering how much worse a truly extreme event can look when the conditions line up differently. Back in 1859, a colossal solar eruption, now known as the Carrington event, slammed into Earth with a magnetic field oriented almost perfectly to connect with our own, and it remains the strongest geomagnetic storm ever recorded. Telegraph systems across North America and Europe failed outright, some sparking and catching fire, and auroras were reported as far south as the Caribbean. A storm of that magnitude striking today, in a world dependent on satellites, GPS timing, and interconnected power grids, is the scenario space weather agencies actively plan for, even though an event on that scale remains statistically rare. That's part of why forecasters treat every cannibal eruption and every anti-hail sunspot with this level of caution, even when the resulting storm ultimately lands on the moderate end of the range. Each one adds another data point to models still being refined, models that have to account for magnetic orientation, cloud density, impact speed, and the compounding effect of two eruptions merging into one. Space weather agencies around the world, from the United States to Europe to Japan, share tracking data in near real time specifically because no single country's satellites can watch the entire sun continuously on their own. For everyday life on the ground, the practical guidance from agencies monitoring events like this one stays fairly consistent regardless of a storm's final strength. Airlines, though, occasionally reroute polar flights away from the highest latitude corridors during strong storms, since that's where radio blackout risk runs highest. Farmers running GPS-guided equipment are advised to expect brief accuracy drops rather than plan around perfect signal the entire time a watch is active. And anyone hoping to catch the aurora is told the same thing every time. Get away from city lights, look toward the northern horizon after dark, and be patient. That uncertainty is exactly why agencies like NOAA and NASA keep such close watch on active regions like this one, and why an anti-whale hail sunspot capable of firing 3 major flares in under half a day earns this level of dedicated tracking and public warning. As the sun continues moving through this active stretch of its cycle, more sunspot regions carrying this same kind of unpredictable reversed magnetic complexity are likely to rotate into view, each one carrying its own chance of launching another fast-moving cloud that catches up to one already ahead of it in space. If this kind of space weather coverage is something you want more of, subscribing means you won't miss the next eruption the moment new information comes in. For now, the Cannibal cloud that raced toward Earth has already passed through, leaving behind a run of dazzling aurora displays and a fresh reminder of just how much energy the sun is currently capable of hurling in our direction. But the sunspot region responsible for it hasn't gone anywhere, and neither has the broader stretch of heightened solar activity driving events like this one. Forecasters are already watching several other active regions on the sun's surface for the same warning signs, the same magnetic complexity, and the same potential for another fast eruption catching an earlier one from behind, merging into something stronger and harder to predict than either one would have been alone.